In this video, we're going to study theoretical and experimental probability a little bit further. Excuse me. And in this particular section, we're going to look at a spinner. So we have our spinner here. I went ahead and colored it for you. Yours, of course, is copied black and white, but you can see the letters around the outside. We're going to first talk about the theoretical probabilities on this spinner. So if you remember from the first video in this section, these are your thinking probabilities. These are the probabilities that I can just think about getting inside my head. I don't have to do anything other than think about them. So first thing, the probability of getting a blue section. I notice that I have 3 blue sections out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sections. So it's going to be 3 out of 12. And if I simplify that, it would be 1/4. Next one, what is the probability of getting green? Well, I have 1, 2, 3 green sections out of 12 total sections, and so again, that probability, theoretical probability, is going to be 1/4. Probability of getting a red section, I have 2 red sections here and then 3 red sections here, so that gives me a total of 5 red sections out of 12. Probability of spinning a yellow, I have 1 yellow section out of 12. Probability of getting a red or a blue, so I have to consider red and blue together. I have 3 blue sections and 5 red sections for a total of 8 out of 12 sections. And if I reduce 8 out of 12, I should get, 2/3. So I have 8 out of 12 sections are either red or blue, and that simplifies down to 2/3. And the probability of a not green section, so that's anything but green. So I know I have 3 green sections, which means that leaves 9 sections that are not green out of 12, which simplifies to 3/4 of my spinner is not green. So notice I didn't actually spin the spinner. All I did was think about, based on the picture, what these probabilities should be in an ideal situation. All right, which color is most likely to be spun? Well, this is the one that has the highest probability, and in our case, that would be red. Which color is least likely to be spun? This is the one with the least amount of sections, and in this case, that would be yellow. Which colors have an equal chance of being spun? Well, in this particular spinner, both blue and green have a probability of 1/4. So that would be blue and green. Name a pair of colors that have a 50% chance of being spun when considered together. So I have to think about 2 colors that take up half the spinner when I consider them together. And there's 2 possible answers for this. Blue and green both take up 6 out of 12. Or so do red and yellow. They both take up half of the spinner. What is the difference between the theoretical probabilities of spinning a red and spinning a green? So difference means subtract, and I'm starting with red and then I'm subtracting green. So the probability of spinning a red is 5 out of 12. The probability of spinning a green is 3 out of 12. And if I subtract, 5 minus 3 is 2. And when I subtract fractions, the denominator stays the same. Hopefully you remember that from 6th grade. And that's going to be 12. And if I simplify that fraction, the probability difference is 1/6. So that was all theoretical. Again, no spinning actually occurred. All right, so now we're going to move on to some experimental. So here's our experimental example. Suppose Susie spun the same spinner in a super simulation. Simulation is another word for experiment. We're going to use her results to determine the experimental probabilities for each color. So I now have to use the table. This is a data table or frequency table. When you're doing experimental probabilities, you're almost always going to have some sort of a table. The first thing you're going to want to do is you're going to want to find the total number of spins. If it's a spinner, rolls, if it's a dice, you need the total in order to calculate these probabilities. So we're going to add up all of these. 13 plus 12 plus 19 plus 6. And we get 50. So there's a total of 50 spins. All right, so we're going to get the probability experimental of spinning, or a blue, is going to be 13 out of 50. Probability of getting a green, 12 out of 50. Notice these are no longer out of 12. These are out of the total number of spins. I can simplify this to 6 out of 25. Both pieces are divisible by 2 in that fraction. Probability of getting red, 19 out of 50, cannot be simplified. Probability of getting a yellow is 6 out of 50. Again, I can divide both numerator and denominator by 2 to simplify to 3 out of 25. Probability of red or blue, so I have to add these up together, red and blue. So I have 19 plus 13 gives me 32 out of 50, which I can then simplify to 16 out of 25. So again, both of these are divisible by 2. And then probability of not green, so I need to add up everything except for green. So 13 plus 19 plus 6 for the blue, red, and yellow. That gives me 38 out of 50. And if I divide both of those by 2, I'm going to end up with 19 out of 25. All right, so now I've got all my experimental probabilities. Notice these came from the data table. I actually used the data. I have to conduct an experiment or a simulation or some sort of data collection. All right, number 5, which individual color has an experimental probability closest to its theoretical probability? The easiest way to answer a question like this, and yes, there have been questions like this on state tests. They've released several questions that are similar to this. The easiest way to do this is to go through and make a chart of your different colors. So I have blue, green, red, and yellow. And I'm going to compare the theoretical and the experimental. So I'm setting up a table here. Again, this is the easiest way to do this, and it does take a little bit of thinking, a little bit of problem solving, and a little bit of organization here. So if I look back at the top, my theoretical probability of getting a blue is 1/4, right there, 1/4. So I'm going to fill in 1/4. Green, go back up to the top, is also 1/4. Red was 5/12, and yellow was 1/12. And then if I go to my experimental, which I just calculated a couple seconds ago here, my experimental probability of blue is 13 out of 50. The experimental probability of green is 6 out of 50. Experimental probability of red is 19 out of 50. And the experimental probability of not green is, of yellow is 3 out of 25. And blue is 6 out of 25, not 50. My apologies there. All right, so as you guys learned in 6th grade, it's really hard to compare fractions if they're not either in the same denominator or converting them to decimals. So at this point, it's probably quicker to convert all of these to decimals, and you probably already know a couple of these. 1/4 as a decimal is 0.25. So I can go ahead and convert those. To convert a fraction to a decimal, you take the numerator divided by the denominator, so we can quickly do 5 divided by 12, and we'll get 0.4167. I did round that a little bit. 1 divided by 12 is 0.0833. 13 divided by 50 is 0.26. 6 divided by 25 is 0.24. 19 divided by 50 is 0.38. And 3 divided by 25 is 0.12. And then I have to compare. So how far apart are these? So these two are only 1/100th apart. These two are only 1/100th apart. These two, they're a little less than 1/10 apart. And these two, those are a little less than 1/10 apart. So really, my two that are closest in theoretical and experimental are going to be blue and green. If you wanted to find exact values, you could subtract. experimental minus theoretical or vice versa. But here we can just kind of eyeball and compare 1/4 and 0.26 are pretty close, and 1/4 and 0.24 are also pretty close.